Okay, we were at section 34.6, dispersion. And let's go to the PowerPoint. And there's a graph here. This is figure 3420 in your text. And you can see that they have crown glass, acrylic, fused quart. And you can see the crown glass has a index of refraction around 1.52, acrylic about 1.495. I'm just using an average, and the fused quartz about 1.465, something like that. But the thing to notice about these is that the index of refraction is color dependent, wavelength dependent. In other words, the velocity varies with color. With the violet end of the spectrum, there's more refraction than on the red end of the spectrum. You can see that the red end of the spectrum, at 700 nanometers, the index of refraction is lower. I mean, just look, if you look at the acrylic, the red is about 1.49, and at the violet end of the spectrum, it's about 1.51. So you can see that the index of refraction is color dependent, wavelength dependent. So the colors in the refracted beam, white light contains all colors of the spectrum. The colors in the refracted beam are separated because dispersion in the prism causes different wavelengths of light to be refracted through different angles. And the same thing happens with a rainbow. When you have a rainbow, you have the sunlight coming through the droplet, and there's multiple factors going on here. The one you have first is the light comes into the water droplet, and water droplets are spherical. They're not teardrop shaped the way they're shown in common images. So the water droplet, as it enters in, it's the index of refraction of water, so the lights get bent. The red makes an angle of 42 degrees, and violet makes an angle of 40 degrees. But you can see that this is when it enters and exits out. But you can see it enters in, it is reflected off the back side of the drop, and then comes to the front side and is the inverse refraction. You're going from water to air. And so what you're actually seeing, the rainbow that you're seeing, is actually taking place inside your eye as it intercepts these different rays coming out of the droplets. So the highest intensity light traveling from the higher raindrops toward the eyes of the observer is red, whereas the most intense light from the lower droplets is violet. So you can see you have the drops that are at the top, you can see the red is intercepted by your eye, but the violet and other colors go above your head. And by the time you get down to the violet, the red and all the other colors are below your head, below your eyes. So what's actually happening is you're seeing the rainbow is being formed inside your eye. Now everybody is, this person standing next to you is going to see the same thing. And the reason you see the circular pattern is because of your iris, the shape of your iris. If we happen to have square irises, you would see a square rainbow. All right, double rainbow is when you see a double rainbow, you're getting the incident ray coming in, reflected off the backside, reflected off the front side, reflected off the backside, and back out. So you get multiple reflections, and it reverses the colors of the rainbow. And they're always fainter because you've got you lose some intensity. Okay, and there's some why isn't it showing these? Oh, there it is. The Heiligenschein is the let me. Well, I forget what it is. Just like from looking at dewdrops in the morning, and I forget how they explain it. I'm not really familiar with this, but I'll read what it says. When you glance at your shadow at dew encrusted grass, you're observing Heiligenschein. It's an effect due to the retroreflection from the spherical dewdrops on the uh, on the grass or on the just from the dew that's on the foliage there. Man, why? Let's go back and now I don't know. I don't know why it's not. Oh, there it is. Just have to play with it a little bit. I don't know why it's acting like that. Where you have um, pastel colored bands below the rainbow, it's due to the interference of the waves. Um, and the sun dogs, sometimes you see a halo around the sun, and those are from ice crystals. Often you can see it around the moon if you have just a haze of ice crystals uh, in the sky. You see this beautiful circle around the moon, and you can see it around the sun also, called sundogs. And then mirages. Mirages, well, light coming at a very shallow angle. You have the warm road, so the light coming off the uh, at a shallow angle passes through the warmer air on the road and is constantly refracted and so actually misses the road and comes and hits your eye. So you're actually seeing a reflection, or you're seeing the sky that hasn't bounced all the way down, and it's hitting your eye. It makes it look like it's wet. We've all seen that on hot Texas roads. I'm sure that where it looks like the road is wet, you get up to it and it's dry. Okay, let's see. In photography, lenses in a camera use refraction. I need to move this out of the way. So, in photography, lenses in a camera use refraction to form an image on a light-sensitive surface. Ideally, you want all colors in the light from the object being photographed to be refracted by the same amount. Of the material shown in the figure, which would you choose for a single element camera lens? Well, if you look at crown glass, there's like two or 0.2, I'm sorry, 0.02 difference from the red to the violet from it looks about the same for acrylic, but for fused quartz, it's just a little bit over 1. So the fused quartz has uh, uh, the closest refraction from the violet to the red. So you would want to use fused quartz. Okay, and that ends it for this. We'll finish with total internal reflection at the next one.